A very popular type of question on limits would be regarding L'Hopital's rule. Now, the first step in evaluating any limit would be to plug in whatever your x is approaching into the function. And if you do just that, and you get a value of 0 over 0, or infinity over infinity, then you must apply L'Hopital's rule. These two forms are known as indeterminate forms, which means you cannot basically find the value of the limit with just plugging in. Now, L'Hopital's rule is as simple as follows. You simply take the derivative of the numerator and the derivative of the denominator, and then try plugging in your a. If you still get the same answers in indeterminate form, you apply the derivative again, and perhaps even again. You keep going until you get an exact value. So a quick example would be, find the limit as x approaches 1 of x minus 1 divided by ln of x. Now, as we must do with limits, let's try plugging in first. 1 minus 1 over ln of 1. Oops, pen's running out of ink. So if we have 1 minus 1, which would become 0, and ln of 1 is still 0, this right here is an indeterminate form that should be familiar to you and would remind you of L'Hopital's rule. So this cannot be solved by any other method. So if we take the derivative of the numerator, which would just be 1, derivative of 1 would be 0, and the derivative of the denominator, ln of x, which is 1 over x, we can further simplify this as 1 multiplied by the reciprocal of the denominator, which is x, which then becomes x. And then we can simply take the limit of our new function. So the limit as x approaches 1 of x would simply be equal to 1. And that is our answer through L'Hopital's rule. A slightly more complicated example here. Find limit as x approaches 0 as tan of x minus x divided by x cubed. First step always, let's try plugging in. Tan of 0 we know is 0. X as limit x approaches 0 of x would still be 0. And if we take the limit of x cubed as x approaches 0, it would also be 0. So we get 0 over 0, the indeterminate, the very dreaded indeterminate form. Now we take the derivatives of the numerator and denominator, of course, separately. So the derivative of tan of x would be equal to secant squared x minus 1 over the derivative of the denominator would be 3x squared. This is our first derivative, of course. Now let's try taking the limit as x approaches to 0 to see if we get an exact answer. Secant squared of 0 would be 1. Minus 1, we get a 0 in the numerator. 3 multiplied by 0 squared is still 0. It's that same answer again, so we are still in L'Hopital's rule. Let's take another derivative now. The derivative of secant squared x would be 2 times secant of x times secant of x tan of x, the derivative of the inside of the bracket, minus the derivative of 1, which is just 0. All of that divided by 2 multiplied by 3, which is 6, and x. Now let's try taking the limit as x approaches 0 of this function. Secant of x as x approaches 0 would be 1. Tan of x, however, we know as 0 is still 0. That would make this entire value 0. So in the numerator we have 0 minus 0. And the denominator, 6 multiplied by x as x approaches 0 would be 0. And it's that same 0 over 0 again. So let's go on to L'Hopital's rule again. Hopefully it works out this time. We've got a tough function on our hands now. So the derivative of 2 secant x tan x, I've actually calculated it beforehand, so don't think I'm super smart coming up with this, plus tan of x times 4 secant x times tan of x, and then the derivative of the denominator separately would be just 6, and the x would disappear. Now taking the limit of this, well actually we could simplify this before taking the limit, so let's do just that. Secant squared x times secant squared x would be secant to the 4x. And right here we'll have tan x times tan x as tan squared x. So plus tan squared x times 4 secant squared x, I've made a mistake here, divided by 6. Now let's try taking the limit. Hopefully this works out. So 2 times secant of to the power of 4 of 0, which we know is 1. So 2 by 1 we have 2. Plus tan squared of 0 is 0. That makes the entire thing 0. Divided by 6. That is equal to 2 over 6, which could be simplified as 1 over 3. So through L'Hopital's rule, we know that the limit as x approaches 0 of tan of x minus x divided by x cubed is just 1 over 3. Okay. Now on to two other indeterminate forms that are often associated with L'Hopital's rule. The first one, if you have two functions being multiplied by each other and you either get 0 times infinity, infinity times 0, 0 times negative infinity, or negative infinity times 0, then you must take the reciprocal of either of f of x or g of x and set it as a denominator of the other. I know it sounds complicated, but let's just solve this through an example. It would be pretty simple, really. So first step always, the question limit as x approaches 0 from the right of x times ln of x. If we plug in, we get 0 multiplied by ln of x as x approaches 0 from the right. We know the graph of ln of x looks like this right here, so it's approaching negative infinity. Now this is an indeterminate form we've just discussed. So in this case, we must take the reciprocal of either x or ln of x and set it as the denominator of the other. Let's take the reciprocal of x right here. So we'd have 1 over x and set it as the denominator of the other function. So what I'm saying is we'd leave ln of x as it is, take the reciprocal of our first function and set it as the denominator. Simple math trick. Now let's apply the same limit. Ln of x as x approaches 0 from the right would again be negative infinity. And 1 over x as x approaches 0 from the right would be negative infinity. Now does this look familiar? Yes it does. It is L'Hopital's rule right here. If you recall, L'Hopital's rule must be applied for 0 over 0 or infinity over infinity. So we take the derivative of the numerator and the derivative of the denominator separately now. The derivative of ln of x we know is 1 over x, and the derivative of 1 over x would be negative 1 over x squared. So all that divided by negative 1 over x squared. Now let's apply the limit. Well, we could simplify it before applying the limit, so let's do that. Apologies. This would become just 1 over negative 1 over x, the x's cancel, and that further becomes just negative x, really. Limit of negative x as x approaches 0 from the right, and that is simply 0. The last type of indeterminate form is, well, I don't know what to explain about this, negative infinity minus negative infinity.